Today we are going to cover section 4.1, graphs or polynomial functions. Take the time to write down your title, your essential question as well. How do you sketch graphs of polynomial functions? Take the time to paste your cutouts. Go and pause it, and we'll start once you are ready. Polynomial functions. Let n be a non-negative integer where we have n is our largest exponent. We don't want it to be negative. We also don't want it to be 0. And we are laying a sub n, a sub n minus 1, sub a sub 2, and so on. We want them to be real numbers. So therefore, the coefficients will be real numbers. Therefore, that function of x with degree n is a polynomial function. And we see that the degree of the polynomial is the largest exponent of the polynomial. The graphic polynomial function is continuous. It has smooth rounded turns. It has no breaks or no sharp turns. We are going to be talking about absolute and local extremes. Let C be in the domain of P. So therefore, we are going to be looking at specific C, which is the domain, so a specific x value. And we are going to have the absolute maximum, absolute minimum, local maximum, and local minimum. Now, the absolute maximum, P of C is an absolute maximum if that is the largest value. Now, when we talk about P of C, remember we are talking about the y value, correct? So if we look at this graph, the maximum, we know that this is the maximum, but there are other values that have a larger y values, other points that have larger y values on the graph. And that's what it says. If P of C, the y value for C, when you plug in a C, it has to be greater than all the other y values of x in the domain of P. So therefore, this is not an absolute maximum. The same goes for the absolute minimum. This is not the absolute minimum because there are other points that have less value, that are lower, such as this one. So therefore, this one is the absolute minimum. If we look at the next graph, this is not the absolute maximum because there are other values for x that if you plug them in, you get a higher value. And this is not the absolute minimum because there are other values for x, such as here, that if you plug it in, you get lower values. Local maximum is that you can restrict the interval, or maximum, you can restrict the interval to a specific domain, and if that is the highest point in that interval, that is called the local maximum. Therefore, this will be, if we restrict the domain to be from, or the interval to be from here to here, therefore that is the local minimum. So therefore, this will be the local minimum, maximum. And this one will be the local minimum. And that's basically what it's saying here. The local minimum, if you have an interval from here to here, when you plug in the C, that will be the lowest values in the specific interval from x to 1 and x sub 2. So let's go through example number 1. But before we do that, let's go through one more cutout. Go and paste it, paste your graphs or copy them down, and we'll start once you're ready. Go and pause it. So end behavior of a function. The end behavior of a polynomial functions graph is the left-hand side behavior of the graph, as x approaches negative infinity. So whenever you see this notation, we read it as x approaches negative infinity. So therefore the little arrow means approaches. And that's on the left hand side. On the right hand side is when x approaches positive infinity. And I guess I did this last year as well. So let's go and describe the end behavior of this first graph. So we are going to have to do the left hand side behavior and the right hand side. So this is your x-axis. We know that there are negative values to the left, and we know that negative infinity is on the left. And if you continue towards the right, positive infinity will be on the right. So we want to know what happens as x approaches negative infinity and what happens as x approaches positive infinity. So let's work on positive infinity first. And there are two ways that we can write it down. The way that we're going to write it down, we're going to say as x approaches positive infinity, we can just say infinity. Then f of x is going to approach. So therefore, remember, f of x stands as the y value. So the y value, as we go towards the right, the y value continues higher and higher and higher. So therefore, it's going to approach positive infinity. And now we're going to do another statement for the left-hand side behavior. So as x approaches negative infinity, f of x will approach. So as we go over to the left, the graph is going to negative infinity. Now there are going to be times that they might write it down backwards. So they might, well, it's not backwards, just in a different way. So it'll be as f of x approaches positive infinity, as x approaches infinity. So you might see it that way, but it's basically the same thing. For my purposes, I prefer to write it down in this notation. I feel it's a little bit easier to understand. So therefore, let's go through this. Let's go and label your x-axis. On the left will be negative infinity. On the right will be positive infinity. So go and write down your end behavior. Let's go and set it up. So we have as x approaches positive infinity, and we can place a plus in here, but we don't have to. F of x is going to approach, and as x approaches negative infinity, I do need the negative, f of x is going to approach. Go ahead and pause it, see what you get, and we'll compare our answers. Go and pause it. So excellent. In this case, we know that they both are approaching positive infinity, which makes it much easier, right? So therefore, as x approaches positive infinity, on the right is going to positive infinity. And on the left is going to positive infinity as well. Example number 2. Go and copy it down. And we'll do it together because we want to do it algebraically. Where on example number 1, we did it graphically. We also want to be able to understand the algebraic process. Go and copy it down, pause it, and we'll start once you're ready. So for example number 2, some of you guys might want to do a sketch to be able to describe. So if they give you an equation or a function for x to the third plus 5, you know that this is to the third power, so it should be 1, 2, and 3. And then from there we can say on the left is going to negative infinity, on the right is going to positive infinity, correct? But we also want to be able to understand, and notice that's very similar to the first graph. So we want to understand on, let's start with the right. So as x approaches positive infinity, what happens to the function? So we also want to understand why there's a graph goes towards the positive infinity. So as we plug in values for x that are greater, so not 1, not 2, not 3, not 4, not 10, not 20, not 30, but think of a large number that we can plug in for x. 100, 1,000, 10,000. But for now, let's go and plug in 1,000. So if we take f of x, but instead of the x, we plug in 1,000. So just imagine moving to the right 1,000 spaces. Where is going to be the point? What is going to be the y value? So 4x to the third power plus 5. And I'm going to plug in 1,000. And now let's go and simplify it. What's 1,000 to the third power? 1,000 times 1,000 times 1,000. It's going to be a huge number, right? How big? Well, it's going to be so big that we're going to say it's going to be infinity. N plus 5. So 4 times infinity will be infinity. Remember, it's going to be 9 zeros. So therefore, this will, we're going to say it's infinity plus 5. So what's that 5 going to do to the graph? Let me just step into the calculator. So we have 10,000, no, 1,000 to the power of 3 times 4. So if you have that, and if you have that much money, and you add $5 more to it, is it going to make a difference? No. So therefore, this doesn't make a difference, so therefore we just have equal to infinity. So therefore, this will will approach infinity. It's not an equal sum, but it's a approaches. And the same thing we're going to do algebraically. As x approaches negative infinity, f of x approaches. So let's go and plug in, and on the homework, you also have to show me the process. You can't just sketch it if it's asking you to do algebraically. So if we plug in a negative 1,000 is equal to 4 times negative 1,000 to the third power minus 5, or plus 5. What is negative 1,000 to the third power? Negative 1,000 times the negative 1,000 is positive, times the negative gives you negative. That's going to be so large, we're going to say it's going to be negative infinity. Times 4 plus 5. 4 times negative infinity will be negative infinity. Is that 5 going to make a big difference? No. So therefore, that'll be negative infinity. And that's how I want you guys to think about it. I want you guys to be able to think that what's going to determine that in behavior will be the largest exponent. And the reason why is because that number is going to become so huge that this is not going to make a difference to the graph. So the only thing that we're going to be looking at to determine the end behavior will be the first term. Do you agree? So let's do the same thing for the second one. And let's remember that this and this is your answer. This is the left-hand behavior, and this is the right-hand behavior. So we have, as x approaches positive infinity, f of x will approach, and as x approaches negative infinity, f of x will approach. So now let's go and plug in a positive 1,000. Or you can plug in a bigger number if you want. So f of x, where x is going to be 1,000, is going to be equal to negative 2, 1,000 to the fourth power plus 7 So what is going to be driving the power or the value of f of x? It's going to be this term, right? Because 1000 to the 4th power will be positive or negative infinity. This is going to be negative 2 times positive infinity plus 7 times 1000 is going to be 7000 plus 1. So therefore, this will give me negative infinity plus 7001. Will this make a difference? No. So therefore, that'll be negative infinity. And we'll be doing the same thing for here. We are going to plug in a negative, huge negative number. So it's going to be a negative 1000. And this will be equal to negative 2, negative 1000 to the 4th power plus 7, negative 1000 plus 1. And I'm just going to simplify. So therefore, negative 1000 to the 4th power, is that going to be positive or negative infinity? Whenever you raise it to an even power, it's going to be positive. So negative 2, and this will be positive infinity. This will be, will this make a difference? No. So therefore, this will be just negative infinity. So let's continue to example number 3. So take the time to paste your cutout. Take the time to read through it, and also paste example number 3, and we'll start once you are ready. Go and pause it. So the leading coefficient test. As x moves without bound to the left or to the right, the graph of the polynomial function eventually rises or falls in the following manner. So we have two cases, when n is odd or when n is even. Now n is going to be the degree of the polynomial, so in this case is to the 3rd power. When n is even, they give you the example of to the 4th power. And if it's odd, you know that it will be from negative infinity all the way to positive infinity, or vice versa. But whenever the degree of the polynomial is even, they both will be positive infinity or both will be negative infinity. Now, something else to be able to keep in mind is that if the leading coefficient is positive in A stands for any number, then on the right hand side, your f of x will go towards positive infinity. And if the leading coefficient is negative, then it will end in negative infinity. And the same thing will be even if it's even. Positive will end in positive infinity. Negative will end in negative infinity. So therefore, if it's odd and if it's positive, it knows ends in positive infinity, but because it's odd, it's going to start in the opposite, or vice versa. If it's positive and it's even, both positives. If it's even and negative, both negative. So let's go through example number 3. I'm going to take the time to paste all 4 graphs, and then we'll start once you are ready. Go and pause it. So first, we need to be able to determine the degree of the polynomial. And the way we do this is that we can't count the terms or how many different ways it's heading. 1, 2, 3. So therefore, this polynomial should be x to the 3rd power. Now it ends on the bottom, on the right hand side. As f of x approaches positive infinity, as x approaches positive infinity, f of x will approach negative infinity. So therefore, I know that this should be negative. And remember that this is odd, so therefore, will be the opposite. On letter B, I know that they both end on positive infinity, so therefore there should be a even degree, and this will be 1, 2, 3, 4. So therefore will be x to the fourth power. On the right hand side, the function ends in positive infinity or approaches positive infinity, so therefore will be positive in coefficient. Now there'll be a number here, but we'll take care of that on the actual, once we write down the polynomial. So to write in the polynomial, we know that whenever we solve a function, so for example, if you have f of x is equal to x minus 2 and x plus 3, to find the solution, we'll place it equal to 0, x minus 2, x plus 3. Then what will be the solutions? Will be x equal to 2 and x equal to negative 3. Do you agree? So now we're going to be doing the opposite, because this will be representing the x-intercepts. We know that it crosses the x-intercept in this case is x equal to 2. This will be x equal to 0, and this is x equal to 3. So therefore, let's write down the function. We have f of x equals. Now I know that there's going to be a negative coefficient, and we don't know what the number is, so we're going to place it as negative a. This is x equals negative 2. So therefore, this will be x plus 2. The factor will be x plus 2. This will be x equal to 0, so therefore the factor will be, we can place x plus 0, but in this case will be just x. The x-intercept is x equal to 3, so therefore this will be x, the factor will be x minus 3. The only thing I'm going to do, I'm going to move my x over as part of the leading coefficient, the negative a. It will be f of x equals negative a x, x plus 2, x minus 3. So that is one possible polynomial for this graph. And we're basing those numbers according to your x-intercepts. So let's try the same thing with letter B. This is x equals negative 2, x equals to 1, and x equals 1, 2, 3, 4. So now write down f of x equals, it's a positive leading coefficient, so we're going to place plus a. This is x equals negative 2 is the x-intercept, so the factor will be x plus 2. This is x equals to 1, so therefore this will be x minus 1. This will be x equal to 4, so therefore this will be x minus 4. But we have a problem. Do you notice something? Correct. So in this case, this should be x to the 4th, but how many x's do we have? 1, 2, 3. So what happens is whenever it bounces off the x-axis, therefore that will count for 2. And we'll cover that in a few minutes. So therefore, when it bounces, it'll count for 2. So we're going to say that this is x minus 1 squared. Or we can rewrite it as x minus 1 and x minus 1. So therefore, this is one possible polynomial for this function, for this graph. So try letters C and D and see what you get. And then we can compare our answers. Composite. So for letter C, in this case, we have x equal to negative 2, x equals 1, x equals 3, and x equals 5. Now let's see, this should be odd degree. You agree? So I know that this should be x. On the right hand side, it approaches negative infinity, so therefore that should be a negative. And that what should be the exponent? 1, 2, 3, 4, 5. Do you agree? So therefore, let's write. I'm going to try to write a little smaller since we have quite a few. F of x equals, that's a negative, so I'm going to place a negative a, where the a can be any number. This will be, the first factor will be x plus 2. Second factor will be x minus 1. The next one will be x plus 3. The next one will be x minus, not x plus 3, x minus 3. And the next one will be x minus 5. We have 1, 2, 3, 4, but we need 5. So where does that one come from? Correct. When it bounces, that one will count for 2, so therefore that will be squared. Now, if we actually want to find the value of a, then we can take any point, and let's say this point here, and then plug in the value of y, plug in the values of x's, and solve for a. But we're not doing that yet. For letter D, what did you get? Let's see. This should be 1, 2, 3, 4, correct? And it should be an even degree. So therefore, it should be x to the 4th. The end behavior on the right-hand side is negative infinity, so therefore that should be negative. And let me write down right below. So therefore, we have f of x equals, that should be a negative a. Then we have x equals negative 3, x equals 0, x equals 2, x equals 3. So 1, 2, 3, 4. So we'll notice that there's no balancing, so therefore there are no multiple roots. And now I'm going to place my x equal to 0 first as just x. Then this will be x plus 3, x minus 2, and x minus 3. Do you agree? Perfect. So take the time to copy the callouts for the zero or polynomial functions and repeated zeros. Read through them. This will be kind of covering what we did on example number 3. And we'll start once you are ready. Pause it and be sure to read through them. Excellent. So zeros of polynomial functions. The function f has at most n real zeros. So therefore, and the keyword is at most, correct? So therefore, if your exponent is of the degree of the polynomial is 3, then you should have 1, 2, 3. But it's at most. So therefore, if the degree of the polynomial is 4, you have 1, 2, 3. The most I can have is 4, but I can have less, and that'll be due to the fact that this gets counted twice. The graph of f has at most n minus 1 turning points. So what are turning points is the question. Is how many times, if you're driving through it, how many times are you turning? So for example, if the degree of the polynomial is 3, then you'll have, according to this, 3 minus 1 will be 2 turns. It will be 1 turn, 2 turns. If the degree of the polynomial is 4, you will have 4 minus 1 will be 3 turns. 3 turns. 1, 2, 3. If the degree of the polynomial is 5, you should have 4 turns. 1, 2, 3, 4. If f is a polynomial function and a is a real number, the following statements are equivalent. So very similar to what we did on example number 3. X equal to 0, x equal to a is a 0 of the function. x equal to 0 is a solution. So a 0, another name for a 0 of a function, is a solution. Another name for a 0 is also the x-intercept. Do you know another name? There's one more x-intercept. There's one more way that we call 0 solution x-intercepts, or yes, sometimes we call them a root. And then the last one is x minus a is a factor, just like we talked about in example number 3, or the polynomial. Now for the next scala, we also have talked about the repeated zeros. So a factor x minus a, where we have an exponent such as to the second power, and we want it to be greater than 1, yields a repeated 0, x equal to a with multiplicity of k. So therefore, we say that this x minus 1 has a duplicity of 2. And if k is odd, then the graph crosses the x-axis at x equal to a. If k is even, then the graph will touch it. So the difference is between whether it crosses it or whether it touches it. So therefore, notice that in this case, whenever it bounces it, whenever it says touches, we're going to call that it bounces. So whenever it bounces, that counts as 2. Or it can also be a 4. Every time it bounces, can be just 2, can be 4, can be 6. We're not too sure what that number will be, but we know that it's going to be even if it bounces. Now, if it crosses, then the multiplicity will be odd. So in this case, it's x minus 4, x equal to 4. Therefore, there'll be 1, or it can be a 3, or it can be a 5. So if it bounces, that means that it's going to be an even exponent. If it crosses, it's going to be odd. So let's go to example number 4. Find all the real zeros of f of x, copy it down, and we'll start once you are ready. So find all the real zeros. So we have f of x equals x to the third minus 12x squared plus 36x. So the only tools that we have so far is to be able to factor this out. So therefore, since I need to find the zeros, I'm going to let f of x equal to 0. And now I'm going to factor this out. First, take a common factor. There is no number here, but I notice that they all have an x, so I can factor a x out. And what's left behind? X squared minus 12x plus 36. At this point, you should be able to know that this, what is this called? This is a trinomial. This is a perfect square trinomial. Because once we factor it out, there'll be x and x. Factors of 36 will be 6 and 6, both positives or both negatives. In this case, they need to add up to a negative 12, so the both should be negative. So that's a perfect square trinomial equal to 0. And let me not forget to bring down the x. And now, because they're all multiplying and they're equal to 0, I know that at least one of them should be 0, x equal to 0, x minus 6 equal to 0, or x minus 6 equal to 0. So that one's solved. X equal to 6 and x equal to 6. So therefore, that will be a multiplicity of 2, which means that it's going to bounce. It's basically going to touch it and come back down on your x-axis. And now I just need to graph it. So let's make it just a quick 6 by 6 since I need 6 or a little bigger. They're all positive, so I'm going to make a little more space on my first quadrant. But you want to have more 2, 4, 6, 2, 4, 6. So therefore, my x-intercepts, my zeros of the function is 0, 2, 4, 2, 2, 4, 6, and 6. Now this is x to the third, and my leading coefficient is positive, so therefore it should end in positive infinity, and because it's odd degree, so it'll be 1, 2, 3. Do you agree? Now, one of the things that you also have to remember is your y-intercept. So in this case, there's a plus 0 in here. So this number here will be your x-intercept, or excuse me, your y-intercept will be 0, 0. So that doesn't help us. Now, if you want to find additional points, then I can just use my calculator and plug in values for x. So let's say I want to be able to find additional points for Beth. I can just type in, plug in a 1 to the third power, minus 12 times 1 to the second power, plus 36 times 1, that gives me 25. So you can see how high it goes. Oh, can't see it. Now if I want to be able to plug in a 2 to be able to find out where it goes, then I can actually plug in additional points and plot them if we want to be able to get more specific. And then so it'll be 232 and so on. But for our purposes today, we just want to be able to get a kind of sketch. So I'm going to start from here. I'll go here, come back down, and then this one counts for 2. So therefore, this will be bounds. So it'll be 1, 2, and bounce it from there, so it counts for 2. But if you want to be able to find additional points, we can plot them, but for now, we just want to be able to know the shape. I do also want you guys to be able to find your y-intercept as well. So let's go through example number 5. Take the time to copy it down, and we can work through it together once you're ready. Go and pause it. So find the roots of the function, and then sketch the graph of the function. So let's see, we have f of x equals 4x to the third power plus 20x squared minus x minus 5. So I need to be able to find the roots. Remember, the roots is the same thing as the zeros, same thing as the x-intercepts, same thing as the solutions. So therefore, I'm going to place my y, my f of x equal to 0. And now I'm going to factor this out. First, can I take a common factor? 4, 20, no? Do they all have an x? No. So can I take a common factor? Do you remember how to factor when you have 4 terms? Do you remember? Correct. You have to do it by grouping. When you have 4 terms, we're going to group the first 2 and the second 2. And take out a common factor from the first 2. Number that divides 4 and 20 is 4. And I can take out x squared. And what's left behind? 4x squared times x, 4x to the third, 4x squared times positive 5x. No, just positive 5, right? I do not need another x because the x is coming from the squares. And now, what can I factor out of the next 2? Remember, your other factor will be x plus 5. So therefore, I'm going to factor a negative 1, or just a negative. So negative 1 times x gives me negative x. Negative 1 times positive 5 will be negative 5. Remember that whenever you do it by grouping, those 2 factors should be exactly the same. And now I'm going to group them. X squared minus 1 gets grouped. 4x squared minus 1 gets grouped. And x plus 5 gets written only once. Remember that this is just like distributive property. If you work on it backwards, this distribute the x squared the 4x squared to them both, it's right here. Distribute the negative 1 to them both, it's right here. So therefore, x plus 5 only gets written once. Now, you can still factor this out. What is this called? 4x squared minus 1 is the difference of two squares. So therefore, this can be factored out. Factors of 4x squared will be 2x and 2x. Factors of 1 will be 1 and 1, 1 negative, and 1 positive. Difference of two squares. And now I have my x plus 5. Let me not forget. And now I can use my zero product property. Because they're all multiplying, each of the factors are multiplying, and they equal to 0. I know that either 2x minus 1 equals 0, 2x plus 1 equals 0, or x plus 5 equals 0. And now I can solve each one. Move the 1 to the right becomes a positive 1. Divide by 2 will be 1/2. Move the 1 to the right becomes a negative 1. Divide by 2 gives me negative 1/2. Move the 5 to the right becomes a negative 5. So those will be my roots. One more thing that I need you guys to find is your y-intercept. Now remember that in order to find your y-intercept, you let x equal to 0. So this cancels out, this cancels out, this cancels out, so you end up with negative 5. So your x-intercept will be 0, negative 5. And we're going to use all that information to be able to make a quick sketch. So I'm just going to make a 5 by 5 should be fine. 2, 4, 5, 2, 4, 5. So therefore, 1/2 is one of your zeros, one of the roots, negative 1/2, negative 5. And I know that y-intercept will be 0, negative 5. So it should cross all those 4 points. Now, if we want additional points, we can plug in a 1, a 2, a 3, and all those points in between to get a better graph up. For now, we just need a quick sketch. This is x to the third, and it's positive. So it's positive should end in positive infinity. It's odd, so therefore it should start in negative. And 3. 1, 2, 3. So let's see, we start here, come back all the way down, and so we go up, and probably going to go way up so that we can take some space to come down. And that is a quick sketch. So we found the roots. Sometimes they'll give it to you as x equals, but actually we should write them down as 1/2 comma 0. So let's just say the roots. We prefer to write them down as points, so it'll be 1/2 comma 0, negative 1/2 comma 0, negative 5 comma 0. Example number 6. So for example number 6, we are going to use a graphing utility. We're going to use a graphing calculator, and we're also going to use decimals as well. So take the time to copy example number 6, and we'll start once you're ready. Go ahead and pause it. Excellent. So sketch the graph using a graphing utility. So first we're going to use a graphing calculator. I want you guys to get comfortable with using a TI-84. So I'm now going to y equals, and I'm going to type in x to the power of 5. Now if you have an older calculator, it might show as, if you have the older TI-84 or TI-83, it will show you as that symbol, which is fine. X to the power of 5, move to the right, plus 2x to the power of 4, move to the right, minus x to the power of 3, move to the right, plus x squared minus x minus 4. So that looks fine. Then I'm just going to graph it. Now, notice that this is still working, so you'll see the little processing symbol. This is x to the 5th, but I don't see all 5. So I'm going to zoom out. So I'm going to press zoom, and then I'm going to go down to out, so I can see the entire graph more and see if I can actually see the other turning point. And it says you want to zoom there, you can move to the right, but in this case, I'm just going to zoom there. So notice that we do not see the other turning point. So therefore, we're just going to leave it as that. So let me zoom back in. Zoom in. Also, they also have something called zoom fit. So let's try zoom fit. See if it does a better job of fitting the function. 1, there, 2, 3. No, that doesn't work well. So I go back to standard. Zoom. Standards number 6. I believe that's why I had it before. So you kind of have to play around with the window to see what is the best view. If you want to go higher, then you can go on the window and then say, you know, the Y, actually I want it to be a little higher, so I'm going to say 15. And you can also change the axis, so from -10 to 10, side to side, -10 to 15. I want to see a little higher, so that's why I place at 15. And now I should be able to see the graph. So therefore, let me just make a quick sketch. And when you're doing this quick sketch, I know that's going to go up to, we can also trace it. So if you want to be able to know trace, we can also see how high does it go, up to 10. You can also do other, but for now we're going to leave that. We're going to continue using the graphing calculator. And so therefore, I know that one of my zeros looks to be here. The other one is around 2.5. Then let me zoom standard. Now, if I want to be able to find out what point is there, I can also use the table, second table, and I can say no. And what I'm going to do, I'm going to do the table settings. So we'll go second table settings, and you want to be able to do startup, auto, and auto, and then I want to start it at -5, and this should be 1. So you should have those settings. I'm gonna go back into table now that I changed it. And now I can see that -5 at -2 is 10. 2, 4, 6, 8, 10. -1 is 0, which is perfect. At 0 is -4. At 1 is -2. At 2 is 54. So therefore I can just build my graph. At -3 is -46. So it comes from here, goes up, comes down, collects that 1 point, goes back up, and that's all we're able to see. So now we can actually just answer the question. A, domain. For polynomial functions, your domain and range are going to be all real numbers. Domain, we can plug in any numbers. Your range, it goes from -infinity all the way to +infinity. All real numbers. B, your local extreme, so we have your local maximum. That is at -2 and 10. Your local minimum will be at 0, -4. Letter C, your x-intercepts. Your x-intercept, the first one is we are estimating. Now, in this graphing calculus, it's a little more challenging to do. We actually can find your x-intercept. So let's go through and calculate. So I'll go back into my graph. And if I want to be able to find my, where it crosses here, or if I want to be able to find my local maximum, let's go and find our maximum. So I'll go and calculate, and I will find my maximum. And it says left bound. So therefore I must select a point on the left and a point on the right. Let me go over to the left. Then I must select a point on the right, and you'll see those two little lines, dash lines. That means that's going to calculate your local maximum in between. Now, if you have a TI-84 plus and not a C, you probably don't see those dash lines. You can barely see them here. Yeah, so it's -2 and 10. We're going to round those up. So it's not really -2, 10, but it's close enough. And you can do the same thing with local minimum. You can calculate minimum. You just select a point on the left and on the right. And then just select a point on the left. We'll continue to the right so I can tell that I want the point in between. And you can select that. You can see those two dashed lines. And then it says guess, and I'm going to press enter. And that way it knows that somewhere in between. And therefore that is my minimum. Which is also not 0, -4, but that's close enough for us. Now, your x-intercepts, we're going to be doing the same thing. To find your x-intercepts, we are going to calculate, and we're going to find the 0, or the roots, or the x-intercepts of solutions, but in this case, they label as 0. And we're going to do the same thing. We're going to do a left bound. We're going to find this one first. So we're going to go on the left and on the right. 1, 2, 4. Left is here, and then we go up. So that way it has to be somewhere in between. And therefore my 0 is -2.5, comma 0. Notice that it doesn't give you 0, but it's a number close enough to 0. So therefore, I'll find the next one. I'll go calculate 0. And therefore, I'll calculate this one. So therefore, I'll go left and right. Left is good enough, and right. And somewhere in between, guess, 0. Perfect. The next one will be at -1, comma 0. And there's one more here. So let's find that value. So I'll go calculate once again. See what you get. 0, pause it. So left and right. And that'll be 1.14. So we'll run that up to 1.1. So those are your 3 x-intercepts. Now your y-intercept, we're going to do the same thing. Actually, for your y-intercept, we know that the y value we're going to calculate. We're going to calculate the value when x is 0. It gives us -4. So that is, and you can do the same thing. Let's say you want to plug in a 5 or plug in a 3. You want to plug, let's plug in a 2 to see how it goes. Instead of doing the same thing, this what we did before, so what we did here, plug in a 2 gives you a 32. Instead, once you plug it in here, you can go calculate value, plug in a 2, and it gives you 54. Oh, hold on, what happened here? Probably you guys saw that I made a mistake. That is correct. So now let's see x to the 5th power. You see that? Oh, that was a different one. That's no one. Okay, But you can do it that way instead of just plugging in. Example number 7. Oh, let's do it graphically. Let's do it through decimals, and you can use decimals for this because it's a little faster. But I also want you guys to get used to using your graphing calculator. So if I go through decimals and I just type in, going to start graphing calculator, and I'm going to type in the function. I'm going to type in f of x. Let me get started. F of x equals x to the power of 5 plus 2x to the power of 4 minus x to the power of 3 plus x to the power of 2 minus x minus 4. That is correct. And notice that it's much easier to find all the points, right? We see that this is negative 2.50 x-intercepts. So Decimals has done a really nice job. And then you actually can just go down, or you can also zoom out a bit. And you just find, just as soon as you touch, you can actually just find. So if you want to use Decimals for your homework, it's fine, but you want to get used to your graphing calculator, because that's what you guys will be using in calculus and also in your IP exam for calc. Example number 7. Well, paste your card out, read through it, write example number 7, and we'll start once you're ready. And pause it. So the most important features of the graph of a polynomial functions are its x-intercepts, extrema, local extreme, local, your maximum, your minimum, your end behavior. For this reason, a comprehensive graph of a polynomial function will exhibit the following features. We want to make sure that we can see all the x-intercepts, all the y-intercepts, all the extreme points, and enough points to be able to reveal the correct end behavior. So we just need to be able to graph this function on a graphing calculator and adjust the window to show a comprehensive graph. So let's do it first on a graphing calculator. So let's just go and use your graphing calculator. Y equals, let me clear up what I had before. And we have x to the power of 6 minus 36 x to the power of 4 plus 288 x squared minus 256. And now I can just press graph. And it's going to graph it. And I just see a bunch of lines. So therefore, that doesn't tell us anything about the graph, right? So let's zoom out. Zoom out. And then we can see how high it goes. And then we can start adjusting it. So that doesn't help us, but notice that your x values are zoomed back 6 standard. So your x values are like from negative 10 to 10 will give us a good number, right? Or from negative 7 to 7. Let's go into window, and x will be from negative 7 to 7. No, you can leave it from negative 10 to 10. The y, let's do it from negative 100 to 100, and we'll start playing with those numbers. That's not good enough. So we have to wait until it's done. So let's increase it, the y values. Windows, let's do 200 and 200. Still not good enough. That's getting better, right? We can still see it. So let's do 300. Window. Oh, 3, darn it. I can't do this until it finishes. So did you get it? At this point, you should be able to see it, right? So let's go back. Window. Let's see if DS can do it right this time around. That's still not good enough. That one's fine, right? I can see the y-intercept. I cannot see those local minimums and maximums. So let's say 500. I'm just going to go 500 this time. Oh, 5 again. Let's try once again. 500. Let's see if I can do this. Still not good. Almost there. So let's do 600. I just need to see that one, those two. So window, we'll do 700. Oh, it's 7 again. It's still not good enough. So let me do 1,000. Perfect. So now you can see all the shape of the graph. So that's the one that we're going to sketch. And we're going to do just a quick graph. So therefore, the way that you're going to write it down, you're going to say the window is from -7 to 7, 1,000 to -1,000. And then you can just give me a rough sketch. You can just say, crosses around here, here, and 2, 4, 2, 4, 5. And then here, 3, and 2, 4, 5. So it comes down this somewhere around here. And it's not asking you to find your actual values, so we don't need to list them. You can just make a quick sketch. And that's it. Now on Desmos it's a little bit easier. Now let's see, one more thing I wanted to try on this. Sometimes if you click on zoom and click on fit, let's see if that does it for us. You see this, it's not as nice. So sometimes I do prefer to play around with the X and Y interest, the X minimum, Y minimum, the window. And now let's go and just type it in here. So let me just erase. So x to the power of 6 minus 36 x to the power of 4 plus 288 x to the power of 2 minus 256. And then here you have to do the same thing. You go into the toolbar, and then I'm just going to copy what we did. So I have to take the time. -7 to 7, and I have you see the little red, that means I have an error. -1,000 to 1,000. And you can just copy the graph from there. And in here, you can actually just find the specific points much easier than your graphing calculator, much faster. We can follow the routes. We can also find all the local minimums, where on your graphing calculator, you have to go through a process and do one at a time. And one more. And the last example for today. So take the time to copy the last example, number 8. Read through it, and we'll start once you're ready. Go and pause it. So monthly average high temperatures at Daytona Beach are shown in the table, where January is equal to 1, February is equal to 2, and so on. So therefore, July will be 90 degrees, December will be 70 degrees, and so on. Plot the data and determine a polynomial function to model the data. So we are going to use a graphing calculator first, and then we'll go into Desmos to do the same. I want you guys to get comfortable with both. So I want to go into y. I'm going to clear the equation that I have here. So I'm going to clear. Then I'm going to stat. So I'm going to press stat, and then I'm going to go into edit, press number 1. Now, if you have points there or values in here, I can just go all the way up and press on clear, and then enter. I'm going to do the same thing for L2, clear, enter, it'll clear for you. So now the L1 list 1 will be your month, list 2 will be your temperature. So just go through the process and type everything in. Good. Then L2, type in your temperatures for each month. That should be 85. And 70. I should just make sure that I type them in correctly. So now that I have them here, pause if you need more time. Now I'm going to go into y equals, and I want to be able to plot, so I'll go up and I'm going to press enter. So when I come down, that should be highlighted. And I'm going to graph it so that way it'll graph my points. Now that's what I see now. So let's adjust your window, and we're going to do a manual. Sometimes if I go zoom and then I go into fit or zoom stats, let's say zoom stats. Actually, zoom stat will do it for you. So that's a nice little function. Otherwise, you can go into window and then just adjust. Maybe we want it from -1 to, let's say, just 13 should be fine. Smallest value is 64 all the way to 90. So notice that gives you just a bit more, which is perfect. Now that I have those graphed and I can see the points, now I'm going to go into a regression. I'm not going to calculate a regression. So if you notice, this is not a it looks like a parabola, but then if this was here, I can actually just use a quadratic regression. But in this case, because of the little curve here, we're going to use a cubic regression. So I'm going to go into stat. I'm going to go to the right to calculate. And last time we used a quadratic regression, I'm going to use a cubic regression. So I'm going to press enter. X and Y values are correct. L1 will be your X values. List 2 will be your Y values. I'm going to leave the frequency list blank. I want to store my regression into an equation, and that way I don't have to type it in. So I'm going to do vars. So I'm going to click on vars. I'm going to go to the right, and I'm going to click on 1. Then I just want to store on the first equation. You notice it says y1. Then I'll go down, and I'm going to calculate it for it. It's going to go through the calculation. And notice that this is a cubic. We have a B, C, D gives the values. But since we saved it, if I press Y, those values should automatically be saved on the function. And now if I graph it, it's going to give me a function. Now notice that it goes through most of the points. It's not going to go through every single point, but it's going to go through most of the points or just in between them. And that is a function. So for part A, if you guys can just write down the equation, and I just need 2 decimal places. So therefore it'll be for part A, f of x equals -0.05. And you can get the values from here, or actually, let's see if I go stats, calculate. Let me just go back. No, it didn't save it for me. So let me just calculate once again. So I can get the values from there. So my 0.05x to the 3rd power, b is positive, will be 0.34 x to the 2nd power, c is positive as well, 3.85 x, and plus 62.82. This is it too. So you can just write down the function. Now for part B, use the function to determine the average height in temperature in June. So therefore, I'm going to type in a 6 into my function for June, and I want to see what it gives me. And then I'm going to compare it, because according to this, it should be 88 degrees. Now, since it's already saved for me, There's different ways of doing this. I'm just going to go to graph and I'm going to go into calculate. So second, calculate. I'm going to calculate the value at 6. It gives me 87.11. It gives me 87. And we're just going to use no decimal places since we don't have any decimal places, so will be 87 degrees. And then compare the value, the given value in the table. So the value for the function for June, the June temperature according to the function is 87 degrees compared to 80 degrees on the table. So notice that there'll be a small variation. Whenever you do a regression, it's not going to go through every single point. But now let's take, and that'll be part A and B. But I do want to take the time to do it through decimals, just in case you don't have a graphing calculator. I prefer that if you're comfortable with both, because you'll be using decimals on your SPAC, and you'll be using a graphing calculator on in calculus and in college. So I'm going to type in the table. I'm going to clear everything that's there. I'm going to click add table. I'm going to add the values 1, 2. Notice that if I press enter, it gives me all the values. A little easier. They've done a really good job with decimals, and they continue working on improving it. They always add new features, and for us, it's free. And now, the only problem that we do need to be able to zoom in and out. But in this case, I'm just going to go under here. I know that my smallest y value is 0, so 1, so I'm going to type in -2, so I can see it. My y value is 12, so I'm going to type in 15. My x value is 68, the smallest one, so I'm going to type in 60. The largest one is 90, so I'm going to type in 100. And that way I can see the entire graph. Now that I've done that, let me change the color. I'll change it to blue. Now I'll go to the next function, and I want a cubic. So therefore, I'm going to type in y1, and that's a sub 1. Instead of an equal sign, I'm going to type in this symbol right on top of the tab. And I'm going to type in ax to the power of 3 plus bx to the power of 2 plus, and notice it's giving me an error. So I need to type in x1 and x1 and cx to the 1 plus b. And those should be similar values that are actually the same values that we got. And that's it. If in this case I need to be able to plug in a value, I'll have to type in the function. Let me see if I can do, I don't think to plug in a value, I'll have to retype it, or at 6, I get to just do it this way. I wonder if there's an easy way. I'll look and see if there's an easy way to type this in. I believe that you have to type in the function. I got it with that. There you go, 87.112. So that'll be the same process. The values will be the same. It's a lot easier. In stats, you guys will be able to see the residuals. You can plot them. You can actually talk about the difference between each of the values. But for now, that'll be the lesson for today. Have a great day, and I'll see you guys next time.